So, welcome back to the lecture 18th, where we will be talking about a little bit more about the AFM, and we'll have a recap of Raman and IR spectroscopy, because I realized that we'll be talking a lot while talking about most of these bioelectrochemical and optical sensors about the interaction of light and matter. So, I decided that we will have a reasonable recap, so you can appreciate once again the power of some of these extraordinary spectroscopic tools, because now, as I have been mentioning for last 3 or 4 lectures, that all the instrumentations which are happening, they are all multimodal operations. You have optical, you have electrochemical, you have spectroscopic, you have some of the electronic features of molecules, you have the mechanical aspects of it in one platform. So, let's recap. We finished the last class with the tapping AFM-IR, where we showed that photothermal expansion due to sample absorption causes an increase in the amplitude, that is good to see, and that is what is being recorded, and that's what helps in especially understanding the biological membrane sensitivity and chemical imaging. Now, from here we move on to the contact resonance. Now, here we will talk about, say for example, here is a surface and here you have the beam falling and the beam is reflecting, right? Now, as soon as this cantilever tip moves, so there is a change in the frequency. As you could see here, there is a change in the frequency. So, this is called contact resonance AFM or CRAFM, is a dynamic contact technique. So, again you recollect, and I talked to you about contact, non-contact and intermittent modes. So, you always have to remember which mode are we talking about. In this case, we are talking about the contact mode that makes use of the vibrational behavior of the cantilever while the tip is in permanent contact with the sample. Generally, an increase in the sample stiffness prompts an increase in the contact resonance frequency. It is almost like you see, for example, this is the harder surface, right? You hit something on this, you'll get a much bigger force, versus you hit a softer surface. Say for example, suppose you jump on a sand, you won't get hurt, but if you jump on a concrete floor, you will get hurt because it will force back at a higher force, right? So, the reverse force will be higher, the counter force will be higher. Exactly the same way, when I am mentioning out here that generally an increase in the sample stiffness prompts an increase in the contact resonance frequency. That means if this particular part is higher, then the contact frequency will become higher. Okay, so this is very important for you to understand, and that's how you can figure out whether the surface is softer or a surface is harder. So, especially when we talk about soft and harder surface, mostly these kind of surfaces are biological materials, and much of the harder surface are inorganic systems. So, depending on what kind of samples you are looking into, you have to make a judgment, and based on that you can develop the topography, CR frequency, contact resonance frequency, and elastic modulus of the particular sample. And if you look at CRAFM, the local elasticity of a surface is probed. We are observing the shift in one of the eigenmode resonance frequencies of the AFM probe brought into contact with the surface. The resonance frequencies of the AFM cantilever changes in accordance with the elastic stiffness of the probe sample contact. So, if you look at it, here it is, right. So, depending on the frequency changes. So here you could see the change which is happening out here. Right? Schematic of the CR-AFM measurement setup with a mechanical modulation from the base of the cantilever. Right, what you see as the CR-AFM frequency spectrum, highlighting the shift of resonance frequency in the first two eigenmode from out of contact to contact on silicon surface. SI is here is the silicon surface. So these are the two eigenmode which are being observed out there. Okay. So, and as you could see in the air, and this is hitting the surface. So it is basically moving and hitting the surface and moving, hitting the surface likewise. Okay. Now, when you talk about the CR-AFM, based on the cantilever dynamics, the measured CR frequencies are converted into contact stiffness. So you could figure out what is the stiffness of the surface, which are further used to determine the elastic modulus of the sample tested by applying an appropriate contact mechanics desorption to the two sample contact. This poses a few challenges in terms of unavailable geometrical parameter, the tip shape, contact radius, different surface mechanics across material, adhesion, viscoelasticity, and the need for analytical contact mechanics model for various sample geometries. The analysis of the contact mechanics is done either by an analytical model or numerical calculation in the absence of an analytical solution. Also, the accuracy of CR-AFM measurement is greatly enhanced by using reference material with successive measurements on the test material and reference material of known elastic moduli. This procedure can be circumvent some parameters that are not available for measurement. So basically, what of the easier way is that you use a system about which you have a fairly good idea, known system. So the known system becomes your reference frame. Once you are using the known system, as it mentioned, also using the reference materials out here with a successive measurement, you will be able to detect a newer material in the successive experimental platform. Right. From here, today we will move to the part 2 of this lecture, which is the recap of the Raman and the IR spectroscopy, because these are the two systems which are very widely coupled with AFM systems for multimodal imaging. So let's recap of what is Raman and what is IR spectroscopy. Before I start, what is Raman and what is IR spectroscopy, try to understand few simple things. In terms of interaction with matter, say for example, this is matter, right? And these are the atoms which are constituting the matter. If a light falls, either some of the light will bend and pass through like this, some of it will get reflected, some of it will get scattered, some of it will get absorbed. So either we will observe scattering or reflecting or bending and refracting or absorption, or they will create a vibration in them. They will lead to vibration of atoms. And this vibration of atoms is the basis of both these spectroscopic techniques, which falls under IR, infrared and Raman spectroscopy. Both are vibrational spectroscopy. It is a vibration of the atoms in a matter while you are trying to capture the unique vibrational mode and assign it a chemical nature. This is that interaction of light and matter and the rise of one of the most beautiful field, of analytical chemistry, the spectroscopy. Okay, so having said this, let's move to what is Raman and what is IR spectroscopy. When you talk about Raman, we always have a pride that this was all done by C.V. Raman in the year 1928. So Raman spectroscopy is a popular technique for the analysis of molecular structure and is considered complementary to infrared spectroscopy or IR spectroscopy. Raman spectroscopy is based on Raman effect, which was first identified by Indian physicist C.V. Raman in 1928. The Raman effect is based on scattering of light, which includes both elastic Rayleigh scattering at the same wavelength as the incident light. So there are 2-3 things which could happen. So this is the incident light. So it is scattered at the same wavelength as V0, which is called the Rayleigh scattering, okay, as the incident light, and inelastic, which is the Raman scattering at different wavelength due to molecular vibration. So these are Raman scattering which are not at V0. V0 is the initial, okay. So they are going out at a different wavelength. So these are the two different wavelengths, anti-Stokes and Stokes. You do not need to get into the details of that, but just understand Raman scattering is about a million times less intense than Rayleigh scattering. Therefore, to obtain Raman spectra, it is necessary to prevent, this part is very important, that is very, very necessary to prevent the Rayleigh scattering from overpowering the weaker Raman scattering. So unless you can deduct this, you will not be able to detect this so easily, because this is pretty pronounced Rayleigh scattering. So Raman spectra are measured by exciting a sample using a high intensity laser beam with resulting scattered light being passed through the spectrophotometer. The Raman shift is energy difference between the incident light and the scattered light in the resulting spectrum. The vertical axis is the intensity of the scattered light, and the horizontal axis is the wave number of the Raman shift, which is shown in centimeter to the power -1. And if you look at the Raman shift, what Raman shift is all about, this is a classic example of sulfur. So here you have the Rayleigh scattering. So you have to, as I was mentioning, this is something you have to be careful, because this is the maximum what comes out of it. And this is the anti-Stokes and Stokes Raman shift. The Raman shift is associated with the two different energy band. The shift at wavelength higher than that of the incident light is termed as Stokes scattering. The shift at the wavelength lower than that of the incident light is termed as anti-Stokes scattering. So if you remember, V0 plus, if you look at it, V0 plus V and V0 minus V. So this is Raman scattering, where there is an addition and there is subtraction with respect to V0. So there is an increase and there is a decrease, and these are the two things what you get in the Raman spectra. So you will always see the numbers on one side it will be negative, the other side will be positive, as you could see here. Raman shift positive, and on the other side will be corresponding negative. Okay. Once again, the Raman shift is associated with two different energy bands. The shift in the wavelength is higher than that of the incident light is termed as Stokes scattering. The shift at wavelength lower than that at the incident light is termed as anti-Stokes scattering. And as an example, Raman spectrum of sulfur measured with an excitation wavelength of 532 nanometer, green laser is shown in figure. Stokes scattering is observed in the lower wave number, longer wave number region, and anti-Stokes scattering in the higher wave number, shorter wavelength region. Typically, higher intensity Stokes scattering peaks are used for analysis, but anti-Stokes peaks are also used. So remember, generally when we report as the higher intensity ones, but sometimes the lower one are also used. This is how the Raman shift happens. So V0 plus and V0 minus, which is Stokes and anti-Stokes. Now, what is the difference between Raman spectra and IR spectroscopy? This is another very interesting part, because many a times I still remember, I always used to get like, I used to almost think at one point that they are all almost same, they are all vibration, but it's not really true. There are very distinct differences, and today we are going to nail down all those distinct differences, right? So if you look at it, both Raman spectroscopy and IR spectroscopy are based on molecular vibration. As I mentioned, these are both are based on molecular, illustrated below out here. What is being illustrated out here, right? Infrared spectroscopy is based on absorption of light energy. This is very important for you to understand, corresponding to the vibrational energy of the molecule. Where it vibrates, it actually absorbs the light, right? Raman spectroscopy is based on scattering of incident light at an energy shifted by vibrational energy, h nu, of the molecule. So this is the very basic difference. One is, suppose there is, say for example, assume the atom as a ball out here. One, a light is falling on it, and it gets absorbed and it starts to vibrate. The other one, it gets scattered and it is to vibrate. It is almost like you hit the ball and the ball is vibrating, or you grab the ball, you are absorbing the energy and still it is vibrating. So these are the very fundamental difference. So if you look at the slide, you will realize this is IR where it is getting absorbed out here, and this is the Raman, which I have already talked about, and Stokes and anti-Stokes, right? So this fundamental difference has to be very clear for all of you, that these two are different. Now when you talk about Raman versus IR further, though both are forms of vibrational spectroscopy, IR and Raman will differ in some fundamental aspect as shown in the next figure. IR spectroscopy is based on the fact that molecular absorption at specific vibrational frequencies causes change in dipole moment. This is the second key difference. IR spectroscopy is based on the fact that molecular absorption at specific vibrational frequency causes change in dipole moment. So this change in dipole moment could be used for detection. Raman spectroscopy relies on the change in the polarizability of the molecule at a frequency, Raman shift, at which the molecule scatters radiation. IR spectroscopy is sensitive to heteronuclear functional groups, vibrations and polar bonds, especially hydroxyl and stretching in water. Raman spectroscopy is sensitive to homonuclear molecular bonds such as carbon-carbon, carbon-carbon double bond, carbon-carbon triple bond. These are good for all the Raman spectroscopy, or if you go for heteronuclear, then you should go for the IR. Mostly, preferentially, this is how they look like. And if you look at the chart, this will give you an overall idea about the upper one, what you see out here. This is all the IR absorption at different zone you could see. So as I mentioned, these are all heteronuclear, hydroxyl, nitrogen and hydrogen, CH3, CH2, CH, and then phenolics, carbon nitrogen bonds. So you look at different part, you could see the different kind of functional groups which could be detected. Whereas in Raman, you see mostly they have a slightly different kind of orientation in them, and this is something which is always used when you are getting the data from IR or the Raman. You have to really refer to the chart that where possibly be, and this has been developed through decades of trial and error and identification and understanding the exact molecular reason why they show that kind of absorption at that particular zone, or why they show that kind of polarizability at that zone, why at that zone they show dipole moment in the case of IR, versus why they show a polarizability at that particular situation of Raman spectra. Okay, so from here, if you look at the complementary relationship of Raman and IR, there is a very interesting thing. So the upper one, what you see is the IR spectra in red, and you have the Raman spectra in blue. They almost look similar, but they are not similar. There are fundamental differences. A comparison of IR spectra and Raman spectra of amino acid L-cysteine is shown in figure. The intensity of the two spectra exhibit mirror symmetry. So IR and Raman spectra are often considered complementary, but they are different in the types of physical phenomena they can measure. In IR measurement, the spectral intensity depends on the size of the dipole moment. As I mentioned, they have a dipole moment for vibrational modes, for bonds such as carbon to oxygen and oxygen to hydrogen. On the other hand, Raman spectroscopy, the intensity depends on the degree of polarizability. So this part is very important, degree of, as I was mentioning in the previous slide, which is essentially electron volume for vibrational mode, and bonds like sulfur sulfur, carbon carbon, carbon nitrogen, you could get a very characteristic signature for them. So you're realizing that why it is extremely essential that we understand these small molecular signatures in order to venture into the world of biodetection, because these are small cues which will help us to detect what kind of things what we are trying to discuss. Okay, so I will close in here, and the next class we will move and we'll talk a little bit more about Raman spectroscopy. Thank you.